we should be very clear about that. Yeah.
Now, Higgs says that it's the end of an era, the standard model now, I mean, probably validated, and the start of a new era. But what do we expect from this new era? What is the scope?
See, the standard model was propounded sometime in around 1980 or even 1960s actually, sorry, not 1980. 67, 68 is when Weinberg and Salam gave the model. And at that time, everything was very poorly understood. Neither the strong interactions nor the weak interactions. Then slowly people started piecing all the pieces of the puzzle together, put them together. And as you are announced just now, there are all these quarks which have been seen. And the top quark was seen sometime around 1995 and people heaved a sigh of relief. The only thing remaining was the Higgs boson to complete this puzzle.
Right.
And the funny thing about Higgs is the theory does not tell you where to look for it.
Yes.
Okay. For example, for top quark, people had a very clear idea where to look for it and how to look for it. But for Higgs, people did not have an idea. So it ranged all the way from something like 10 GeV to 1 trillion electron volts. That was the range. So with great painstaking effort, people narrowed down to 100 to 150 GeV, and now it has been seen at 125 GeV. We hope that it is the standard model Higgs.
Okay.
Now this completes this piece of the puzzle, whatever we have understood. But other things have cropped up. Okay. For example, people believed that neutrinos are massless, but now we know that neutrinos carry mass. And astrophysical observations have shown that in the galaxies, for example, the star's period does not correspond to the matter distribution that we know. Okay. In fact, there is much more matter than what we see. Okay. The invisible matter or the dark matter.
Right.
And obviously, if we are developing a theory to understand all the fundamental phenomena in nature, forces of nature, we have to know that and we have to go beyond standard model. But if
we'll come back to that. We just need to take a quick commercial break. Do stay with us. We are discussing this wonderful, fantastic discovery of a particle that's like the Higgs boson. Do stay with us.
For a happy and productive life, one needs peace of mind. That is why I chose LIC. LIC adds some magical notes of security to life. Then why go anywhere else?
आज तक मैं एक भी ऐसे बच्चे से नहीं मिला who didn't want to fly. And toy planes, they are our most valued possessions. फिर एक दिन हम बड़े हो जाते हैं. We want a lot more speed, thrill, and the ultimate in technology. And of course, गर्व जो महसूस होता है कश्मीर से कन्याकुमारी तक देश की रक्षा करने में. और अपने देश का नाम आसमान से ऊंची ऊंचाइयों तक ले जाने में. सारे जहां से अच्छा. Nothing can beat the feeling जब आपका साथ देती हैं दुनिया की सबसे बेहतरीन मशीनें and the best professionals in the world. Thankfully, I have been there. I know how it feels. और आपकी बारी है.
This is Indian Air Force. Are you up for it?
Welcome back. Professor Shankar, before the break we were talking about dark matter. And, some estimates say that over 90% of space is basically dark matter.
Yeah.
So what can this discovery do to our understanding of dark matter?
The Higgs that we have seen is the standard model Higgs. And what we can now do is direct our efforts to find out there are other Higgs particles which are there in the theory, which can possibly contribute to it. We really don't know what constitutes that. This very beautiful theory called supersymmetry, which tries to simplify fermions and bosons. So once we start concentrating on looking at them, and if we discover more particles, and some of them, it is generally expected to be neutral particle, the dark matter, okay, something like Higgs, scalar particle, then we may be able to understand. If for some reason it turns out that this Higgs is not the standard model Higgs,
okay,
then standard model may be in trouble. But then this can be a candidate, you know that, right?
Right.
So that is the whole idea. So either way, I think it is
new model.
Either way, it is a win-win situation. But
right,
most likely, it is the standard model Higgs that we will know in the next.
And we also now very privileged to have with us Professor R.P. Tandon, the head of the Department of Physics at Delhi University. Thank you very much, sir, for joining us. How would you look at this discovery from the point of view first? I mean that of its impact, and from the point of view that India has also contributed a great deal to it.
Well, no doubt this is one of the landmark discovery after Newton and Einstein, I would say. the very landmark discovery, and India has contributed immensely. For example, from my university, there are at least 5 people who are very actively, they are still there and they are participating in this. There are about 4 students every year which are going there, and we have made some detectors for them. Apart from them, Saha Institute of Nuclear Physics, Bhabha Atomic Research Center, about 7 other universities are also directly involved. Punjab University is also very much actively involved.
Right, and we made some large superconductor magnets and things like that for
No,
this.
we have made a large scale silicon-based detector.
Okay.
Okay, and calorimetrics, which are measure energy of the particles, not the superconducting magnets.
Okay, let's try and understand this, what actually has happened here. I mean, we understand that, particles that probably travel at the speed of light do not have any mass.
Right.
So in contrast to that, what is this new discovery? I mean, how does a particle gain mass?
Well, I'm sure you must have discussed this point.
But we've been discussing other points, but not quite this as yet.
Okay, well, one thing is that everything was there in standard model. We knew everything about. There was one missing link, which was Higgs boson. After all, the fundamental question is, how do we arrive at mass?
Okay.
What gives you mass?
Right.
So that missing link was there. So now we understand if the Higgs boson has been discovered, standard model is going to stay there forever, and we are really not concerned about it. Other thing is we have 4 forces, and the gravitational force is not very well still incorporated and understood. So this will also throw light on, we have 12 fundamental particles, 4 forces.
Okay.
So if this thing is going to be really confirmed,
Okay.
then there will be a lot of scope to go beyond even the standard model.
Okay.
So this will definitely throw, well, it's too premature to say what will be the implication, but the implications will be enormous. But it cannot be a very short range kind of implications.
Right, but how does this interaction, Professor Shankar, take place, between these subatomic particles that, suddenly they gain mass? How does this interaction take place in this field, the Higgs field?
See, in principle, you can always give a mass to a particle. It is not as if you cannot write a mass. But the problem in quantum field theory is that if you want to develop a consistent model, consistent theoretical analysis, we need a very important principle. It's a very sacred principle called the gauge principle, gauge invariance.
Okay.
Now, gauge invariance is known from the time of Maxwell. And the word gauge invariance was coined by Hermann Weyl, a great mathematician. Now, gauge invariance tells us that whatever carries interaction should be massless. For example, electromagnetic interaction is carried by light, photons. Photons are massless. They travel with the speed of light. Light travels with the speed of light.
Right.
Now, we do not know how to build a theory without gauge invariance
Okay.
in quantum field theory. So, when you try to do that, you will only get massless particles which mediate. But in weak interactions, for example, looking at neutron decay, etc., they are not massless. In fact, they are all very short range forces.
Okay.
So it was a catch-22 situation. You want the mass, but then you will have to give up gauge invariance. You give up gauge invariance, you don't know what to do with it.
Right.
The way out of this was actually pointed out through what is called as the Higgs mechanism.
Okay.
Formally, you preserve the gauge invariance in the theory,
Right.
but there is something called spontaneous symmetry breaking that takes place.
Okay.
The symmetry is not broken in the way you write the action, but by the properties of the vacuum. Vacuum is the ground state,
Okay.
and it generates mass. So the way it is generated is you have what is called as a Higgs field. It is the Higgs field that generates the mass,
Okay.
and that mass is given to the mediators.
Fair enough.
And there is one particle which is left out, which we call as the Higgs,
Okay.
and that is what we were looking for.
So then, Professor Tandon, if an object is gaining mass, is it gaining mass constantly, or what? Or is there going to be a time when it's going to stop? Or,
No, it's going to stop somewhere.
right?
Yeah.
But what is that? Is that a definition within the Higgs field itself that it only gains mass? Or, because the theory is that, I mean, if this is going to validate the Big Bang theory, all these planets and stars, etc., are they continuously growing, or what? What is the situation?
Well, we can say the universe is expanding,
Right.
and the mass of Higgs boson is really very large. That itself is enough. I mean,
Okay.
No, the word
Yes.
gaining mass
Gaining
doesn't
mass
mean that it
means
is
growing.
not gaining mass. No.
No.
Is
The
it
word
gaining mass, not
gaining
gaining growth?
mass is to acquire a mass.
Is to acquire mass.
What was initially massless becomes massive.
Okay.
And it has become common usage in physics to say it gains mass.
Okay.
It is not continuously gaining mass. You
It
had
gains
a
mass once and that's it.
That's
no,
it.
it is like that. The
It's
particle
to
is
acquire
there.
mass. Yeah.
Okay.
Particle is there. Now the Higgs field is there.
Right.
As soon as it encounters Higgs field, it acquires mass. But that mass
So
is
those
not
encounters are taking place all the time, isn't it?
No, this. What's it?
No, don't those encounters take place all the time?
Yeah, of course. But the mass is constant after a while.
Okay, the
It's
mass.
not like ever increasing.
Right. No, I mean the confusion is that these interactions are taking place all the time.
The symmetry has been broken.
Okay.
And once the symmetry is broken, these particles have acquired mass.
Okay.
Okay, and they continue to retain that mass. It is like, a magnet.
Okay.
When you cool it below a certain temperature, initially the magnetic north pole and south pole could have been in any direction. But as soon as you cool it for whatever reason, the symmetry gets broken and one direction becomes the north pole and the other becomes the south pole.
Okay.
So that gets frozen after that.
Right.
So that is what happens here.
So, Professor Tandon, now this only talks about the Big Bang.
Yeah.
Is that means that there's going to be no other theory that that physics is going to look at because of this?
Well, people have said that this is just the beginning.
Okay.
That's what the concerned scientists said. This is just the beginning. There will be many more theories. In fact, the physics will undergo some kind of revolutionary changes in certain theories. At least
Such
the
as?
people. I mean, the CERN head has said like this that this is just the beginning. That's what precisely the language is.
Right. So then, what if it is the beginning? And that's a question I had asked you earlier. I mean,
Yeah.
and I think we were interrupted by a break. What is the future?
See, the future is, first of all, we have to understand whatever evidence is coming from astrophysics. There are two kinds of evidence. One is the dark matter, which says that what is visible is only about 4 to 6% or whatever. So there is a vast amount of matter which we don't know anything about. And even more surprising is what is called as the dark energy. The galaxies are all flying away from each other with an acceleration, which is not
Right.
expected. The third major challenge actually for us is that he mentioned the 4 fundamental forces.
Right.
We have a reasonably good understanding of 3 fundamental forces.
Okay.
Gravitational, electromagnetic, weak and strong.
Okay.
Gravity, which is the oldest known interaction,
Right.
Newton of course gave us the universal law. We do not know how to incorporate gravity in quantum mechanics. We do not have a quantum field theory of gravity. Until we do that, in fact, any theory of the universe that we may come up with,
Right.
including Big Bang, it is an incomplete theory.
Okay.
Our
Fair
understanding will be completely incomplete. And in that direction, we'll have to look for new physics, new particles, for example, supersymmetric particles,
enough. Okay.
which are there. Supersymmetry is essential for quantum gravity in string theory, for example.
Right.
So the whole world is open for us now. I mean, it's
We need to take another quick commercial break. There's a lot more to discuss after that. Stay with us.
जल्दी मेरा बैग दो, बस मिस हो जाएगी। लाया भैया लाया।
बाल श्रमिक दंडनीय अपराध है। ये कानून 14 साल से कम उम्र के किसी भी बच्चे को काम में लगाने से रोकता है।
बाल श्रम रोकिए, बच्चों को काम नहीं, पढ़ाई का अधिकार चाहिए। उनकी सही जगह स्कूल है, ये उनका हक है।
आज तक मैं एक भी ऐसे बच्चे से नहीं मिला who didn't want to fly. And toy planes, they are our most valued possessions. फिर एक दिन हम बड़े हो जाते हैं. We want a lot more speed, thrill, and the ultimate in technology. And of course, गर्व जो महसूस होता है कश्मीर से कन्याकुमारी तक देश की रक्षा करने में और अपने देश का नाम आसमान से ऊंची ऊंचाइयों तक ले जाने में।
सारे जहां से अच्छा।
Nothing can beat the feeling जब आपका साथ देती हैं दुनिया की सबसे बेहतरीन मशीनें and the best professionals in the world. Thankfully, I have been there. I know how it feels. और अब आपकी बारी है.
This is Indian Air Force. Are you up for it?
Welcome back. Well, Professor Tandon, before, I mean, this discovery was made, it was all part of a hypothesis. I mean, when Higgs' hypothesis, how does one build a hypothesis which, can ultimately be proved scientifically? I mean, it's what scientists do, but where is it? It's figured out in their mind, or what does they do?
But this has been pretty old problem. I mean, this has been for 40, 50 years.
Yeah, but people had given up and they said, "Where?" That's how they got this name, God particle, because somebody said, "God damn it, where's the particle?" So
well, of course, there are different stories for that. That's not precisely.
Yeah.
But the thing is, as long as you don't have these machines,
right,
it was very difficult to talk about that. You know, America had a lot of plan for starting SLAC and things. All those were cancelled.
Superconducting super collider.
Yeah, super collider.
They had to scrap it.
Yeah, they had to scrap it. So it is only that this machine was inaugurated in 2008. People again started taking interest. But this hypothesis has been sitting there for the last 50 years, I must say.
Right. And how would you look at Higgs's contribution now?
Higgs' contribution was absolutely fundamental because he developed a relativistic theory, his famous 64 paper. But you know, like all discoveries, it is not in isolation. Actually, there was a very seminal paper in 1962 written by Phil Anderson, who is a very great condensed matter physicist, and he was trying to understand superconductivity.
Okay.
And he had already proposed the mechanism. It was non-relativistic. So people did not probably notice it much. And then there is the contribution coming from two gentlemen called Englert and Brout. And there were another three gentlemen, Kibble, Hagen and Guralnik. And what Higgs actually did was to sort of take them all together and develop into some kind of a coherent, put it in a coherent form in his relativistic thing. So in that sense, the credit has to be sort of, I mean, without taking any credit away from Peter Higgs, we should realize that there is a whole lot of people who contributed.
Fair enough.
There were at least 4 people simultaneously.
Yeah. In 61, Schwinger wrote a very important paper called Can Gauge Invariance Be Consistent with Massive Particles? And Anderson was Schwinger's student. So there is a whole history that goes around.
I think Glashow and Abdul.
No, they used this mechanism.
Yeah, they used
this mechanism.
Let's talk about what doors this opens. You know, I mean, some of the concerns one would think about is that there's energy shortage in the world. Could this open new areas of trying to gain?
Well, one thing I must say that it has removed the fear that it's going to be a end of the world, because nothing is that, so that fear is gone at least.
Right.
Now the other thing is, it is too premature to say what will be the implication.
Okay.
But like you said, energy is one sector. They say climate change also it may throw some light, and like he mentioned, antimatter, and there is a technique called PET, positive annihilation experiment. There they say antimatter plays a lot of role. This is what I was just reading one of the article. So there, but as such, it is very difficult to say at this moment, even for scientists. Even scientists say it's too premature to say what are the implications going to be.
Right. We'll have to leave it there. Thank you very much, gentlemen. We've run short of time. It's wonderful talking to you. Well, Bose was one of the greatest Indian scientists, one who was destined to influence Einstein's work. But India's contribution to the Higgs boson discovery goes beyond the maths behind it. You know, India developed and supplied over 7,000 precision magnet positioning systems for the Large Hadron Collider. It also contributed over 1,500 superconducting corrector and correcting magnets, over 5,500 quench heater power supplies. Well, the indoor-based Raja Ramana Center for Advanced Technology developed and supplied various vital components for the Large Hadron Collider. And while CERN scientists may be credited with this huge discovery, well, India's role is actually written in code and in deed. Thanks very much for watching. Namaskar.
Late edition was brought to you by LIC Jeevan Vaibhav.